Right, hi, Matt. So I will try to keep this somewhat short because I think I'm in danger of cutting into lunch. So I'll let the next speaker do that. Okay, so this is the outline of the talk. I mean, basically, I'm going to give some of the motivation and then talk about the core design architecture, which you've heard a few similar talks, and then talk a little bit about the actual emerging device work that we're doing at Sandia. So, and of course, the general topic is using resistive memory to make a more efficient hardware accelerator. So, Sandia just fairly recently began last October a significant kind of multidisciplinary project, which is combining neuroscientists doing algorithms research and then engineers with neuroscientists kind of researching architectures, both with COTS parts and then more novel devices, novel architectures. And then the third kind of big thrust is the actual device work, as well as, so the device work actually spans the area of both the device physics and the circuit architectures and kind of higher level architectures used for neuromorphic computing. So, and it's called the project's called Hardware Acceleration of Adaptive Neural Algorithms, HANA. So this talk is going to kind of talk about some of the preliminary, it's somewhat of a higher level, and anybody who wants to know more can come talk to me later afterwards. Okay, so yeah, I mean, we've seen similar slides to this already, but there's been kind of long interest in neuromorphic computing. There was a big interest in the 60s with the early perceptron computers, although they kind of were debunked, I guess, to I don't know, say it delicately. But there's a lot of excitement now. So there's both the True North resulting from the DARPA Synapse project. There's a lot of interest in it's an SRAM-based chip. And then we heard about the Spinnaker yesterday, as far as a whole system with a lot of connectivity approaching neural scales. So what we're trying to look at now is what's going to be the next generation, so a decade out or so. How are we going to do neuromorphic computing? So first of all, let's look at how we're doing it now. Most, I think, algorithms is fair to say run on either CPU or GPU. We've seen that from Google's deep learning study. The most efficient or more efficient results run on a small GPU supercomputer. There's also, and I mean, the advantage of GPUs and CPUs, of course, they're most general. Everybody knows how to program a CPU. GPUs, more people know, are becoming very common too, and GPU supercomputers. FPGAs are a little more difficult to program, but they're still pretty flexible, and you can implement a lot of kind of interesting networks in them. And then the most expensive kind of current option right now is to have a custom ASIC, usually SRAM-based ASIC. And so that's what came out of the DARPA Synapse project. It's actually one of the biggest chips ever built, and it has about 40 megabytes of SRAM memory that allow the synapses to be stored and computed on, I think, about 1 million neurons, which the neuron, of course, does the computational function. So, as we all know, Moore's law, up until this point, it continues to provide enormous benefits on these chips. Although kind of, one of the issues with Moore's law is we are starting to see the slowing down, and it's actually in a lot of ways because of economic reasons. But what we've gained for free for the last more than 30 years, probably almost 40 years at this point, it may be kind of coming to an end. And so actually, this may be kind of the most important slide of this talk, especially the kind of abbreviated talk we'll try to give here. Is why should we look at a new technology for neuromorphic computing? So, I mean, it's expensive to look into new technologies, and it's a lot of work, and it's going to take a long time. But the biggest issue, and you're seeing that kind of in the True North chip, and just the modern chip architecture is meant to have a very good chip with 40 megabytes or much less usually. I mean, 40 megabytes is about a $4,000 or $5,000 server chip. Everything else has a few megabytes or maybe 10 megabytes of cache. Otherwise, all the energy and all the memory, DRAM memory, is off the chip. And so, I mean, this is a problem that was recognized a number of years ago by the exascale computing community, and it's actually going to affect us here because we want to do a lot of processing. So, I mean, essentially, neuromorphic computing, I think it's reasonable to say that most of the talks I've heard would agree with this, is that you really want to find the most efficient way to connect logic and memory with an efficient routing system. And right now, the most efficient routing system is still a monolithic set of interconnects on one chip. I mean, it's more efficient than at least at this point, than photonic or through silicon vias, although those are very efficient methods of communicating from chip to chip still. So, the advantage of resistive memory essentially is that you could have terabits on a single chip. And so you could actually do a very large amount of computing on a single chip. You're still going to have to go to different nodes, but this will give substantial power savings over either an integrated SRAM or even an integrated DRAM-based chip with stacking. And an example, I think Taha mentioned this morning, that kind of some early simulations have shown more than order of magnitude reduction in power. And I think actually several orders of magnitude have been shown in subsequent simulations by some of these groups. Okay, so the next section I'm just going to talk kind of briefly about some of our design considerations. Right now we're using backpropagation, the kind of standard algorithm, as a sort of straw man to base the hardware on, partly because it's simple, we know a lot of applications for it. Also, though, really you can adapt this to do a number of other like recursive algorithms, STDP, and there isn't a huge change actually. I mean, any algorithm that has a matrix of weights that you need to make fine adjustments on the weights, you can make modifications to what we're going to show you here to do it. So we'll start off here with backpropagation. Backpropagation, a relatively simple algorithm. So I mean, you put, although it does become complicated when you get into hardware, as Professor Taha mentioned this morning. But you have, a training set. So it's a feed-forward network training set. You put your training in, look at the output, go through, calculate all the errors, and calculate the error derivatives in reverse order, and then use that to update all the weights. So the basic kind of resistive memory-based building block looks like this. So you have your neuron that I showed in the last slide, and it basically is a voltage divider feeding into a divider, a amplifier of some sort. And that can either be a binary amplifier giving an off or on output, or it can be, as in a linear network, it can be a proportional neuron. So. And I'm not actually going to go in, the whole subject of neurons is pretty complicated, so I'm not going to cover that in this talk. But this is what the overall circuit would look like. And I'll give some credit to Dr. Taha for he has a very similar, and we've been collaborating with him on the circuit. I mean, this is a basic backpropagation circuit. So what the actual circuit shows is just one layer. So each column there, and I don't have a pointer here, but each column would represent. So each column going down to a neuron essentially represents one set of neurons like we showed on the last page. And so you would have your entire layer of neurons here, and then you're able to actually extract your error sum on the other side, and then feed that back to another layer, which I'll show you how you do a feedback on the next page here. The reason you have two, and I think this was explained earlier too, the reason you have two, though, is so you can have positive and negative weights. So if you only want to have positive weights, you only need to actually have one set of devices there rather than the NOT gate. Okay, so at the system level, you have to figure out how to connect all these together. So what I just showed would end up being one core, and it's essentially one layer, so then you have to have a layer-to-layer connection. So the core itself will update and store the weights of a single layer, and then compute all the error derivatives, which is kind of the center part of backprop. And it also applies the neuron, and the neuron can be any number of different functions. So then you have an entire architecture that you see here, and you have to figure out how to connect them locally. So that's sort of a big part of the design consideration. There's kind of two sort of opposite extremes of how to do this. I mean, one thing is to just have every single core wired off chip, so you can route it to another. You can essentially do any operation you want to it, and that is probably the lowest efficiency way of doing it. And then the most efficiency, of course, is to have everything hardwired. But that's the least flexible design. So there's probably a approach that's sort of in between the two that we'll take. And then another thing is the crossbar size, and this is kind of actually an important thing, the crossbar size itself is probably going to be, in fact, I'm fairly sure from my involvement in the advanced memory community that it looks like resistive memory crossbars are going to have a set size that they need to follow based on the interconnect sizes of advanced nodes and the signal-to-noise ratio. And so that's not necessarily going to coincide exactly with the number of weights that you want in a layer. And so essentially what you have to do is have these connected together, and I think Professor Lee actually showed in her last talk a version of how she's doing this, but you have to have an analog repeater. And so we've designed some analog repeaters that actually will go in between these. I'm not going to go into detail in that, but that's important because as soon as you have to go to an A to D converter, you're using a huge amount of energy, and so you end up wasting a lot of energy. So there's sort of a trade-off on how many, and that's part of the design space study that we're doing right now, is how many cores that you'll have connected by analog repeaters before you actually go to a routing system and then potentially have to make the signals into digital signals. Okay, so now to actually talk a little bit about the devices, which is my own particular area of expertise. So the devices that we're looking at, so there's a number of different kinds of resistive memory devices, but this is a very common one. There's actually a Panasonic product, a microcontroller, that came out that uses these devices last year. So although they're still very researchy, there is starting to sort of emerge into the world, at least in specialized areas. And the device is a metal insulator, metal stack. This is almost the exact device that we make at the Sandia fabrication facility. So the kind of magic layer is this metal oxide. We use tantalum oxide, which is sort of one of the most common. And it's a substoichiometric metal oxide. So a metal oxide likes to have a particular amount of oxygen in it. In tantalum's case, it's Ta2O5 is sort of its natural state. We purposely sputter it such that it has Ta2O4, so it's actually oxygen deprived. And it turns out that you're able, once you do that, to modulate the resistance of this thing by putting electric field across it in different ways. And it's sort of a combined electric field thermal effect, and there's actually still a lot of work on understanding exactly how these devices work. And I think it's not really entirely agreed on in the community, but kind of the basic idea is that you suck oxygen out of it when you have essentially the positive electric field such that it's attracting the negative oxygen ions. And that, as you suck oxygen out of it, that actually makes it less resistive. When you put the oxygen back in, it goes back up in resistance. So that's how these devices are made. And then up in the corner there is the actual bit that Sandia makes. We have a fab that does a CMOS process, and so this is actually the CMOS compatible version of this process, so there's a lot of different ways to make these devices. But this essentially, and the point of this, I won't go through the whole thing, but the point of it is you would have a full CMOS stack and then start from metal 5 and actually create this device on top of it, almost like you would a regular VIA. So it's very CMOS compatible. You can do everything in the silicon fab. All right, so we've done a lot of work in the past on making memories with these devices. Now we're looking more carefully at what we would need for a neural accelerator. The biggest thing that we would like to have for a neural accelerator is a linear dynamic response. So as you pulse this device with, for example, a positively polarity pulse for, say, 1 microsecond, you want each step for it to be roughly equal. So each step change in conductance to be roughly equal. And that is not a natural property of these devices, because as you change them, so as most people know, and there probably is some flexibility on this. I mean, one of the issues is that you don't necessarily want it to waver up and down a whole lot, or go in the wrong direction too many times. So this is the ideal response, and if we can get close to that, I think that these will have some efficiency. So our simulations are actually looking into this right now. Low variability also. I mean, what people are seeing a lot of, and part of this goes back to the fact that we don't understand how these devices work, but they have a lot of both cycle-to-cycle variability, device-to-device, and even read variability, and I'll show that in a later slide. It's also important to have a wide resistance range. The endurance still needs to be pretty high because you're potentially contemplating replacing DRAM with these, and people have shown very high endurance as possible. The retention, though, actually requirement doesn't need to be necessarily 10 years, which is kind of standard for a memory. We really only need to hold it for weeks because we're using this device to train neural networks. Okay, so when you're doing the weight updates, essentially you're cycling through different conductances, and both of these plots on the y-axis are showing either conductance or current, which is read current, which is proportional to conductance. So you want this to be relatively smooth, as I showed, so on the right is one of Sandia's devices. Although this is at a very high conductivity, So we need to actually get the conductivity down. Now on the left, this is a much lower conductivity shown at a conference recently. One of the biggest issues, and you see this in a lot of these devices, is if you can do a number of pulses in one direction, so for example in this case increasing the current for a number of pulses or even decreasing the current for a number of pulses, and then you switch the polarity and you wipe out all of the change that you've had from that last set. So I mean essentially if you have that kind of behavior as you're updating your network, you could lose everything you learned in your weights from one reverse pulse. So that's the type of thing that we're trying to avoid, and we've actually found that we can avoid it in certain resistance ranges. That's oh yeah, the mouse works. So that's what that particular plot is showing, but we need to get that now to lower high resistance ranges, lower conductivity. All right, and then based on time, I'm going to try to go through this a little bit quickly here, but variability and noise are still a big issue. So device-to-device variation, I mean, this shows the initial resistances of devices across a wafer. They can vary by orders of magnitude. But it's starting to look like a lot of that can be solved by sort of manufacturing improvements, thickness variation improvements. Something that's more fundamental is this cycle-to-cycle variation, which this here kind of shows. Just cycling on one device that already has a filament and everything is more or less static for that device, just turning it on and off with the same bias can still result in like a 2 or 3x variability. And so it's not really, I mean, there's no simulation at this point that entirely incorporates that type of data into one of these models, and that's what we're working toward along with our collaborators. And so what we're doing right now is trying to actually find a good way to quantify that variation. And so one of the ways we're doing that is we have a closed loop cycle that gets the device to very close to a particular set resistance. So for example, in this case it's 10K and I believe like 2 or 3K. Gets it very close to those targets. So we developed a closed loop cycling algorithm. Then what we do is do a closed loop on one side, so it gets very close to the target on one side, but then on the other side it has a open loop, which just means that there's a defined pulse voltage and pulse length on the other side. And essentially what this will tell you is if you're starting at a given resistance, what's your spread with a given pulse time and pulse voltage, where can you end up? And it's, as you can see, the dotted boxes kind of show you can end up over a fairly large spread. So we need to incorporate this into device models, and that's one of the important next steps. And so I took a lot of this out. It would have taken a while, but we've spent some time actually looking where this, a decent amount of time looking where this noise comes from. And you can see actually there's thickness variations within a single device, even within hundreds of nanometers or less. There's also, we think, and we developed a model on this, an internal state variation that could be responsible for this. We've also done a bunch of DFT simulations, which I didn't put up here. It was probably a little bit too complicated to go over in the amount of time, but essentially shows that just the same stoichiometry, same set of atoms, but reconfigured slightly different, will actually change the conductivity by quite a bit. So it's still a difficult thing to understand what exactly the noise is coming from. But right now we're looking to see how much noise can be tolerated. Eventually we're going to try to do this at the circuit level, but right now just with a backprop algorithm in Python, we did a kind of simple study just looking if you vary with white noise, if you take the delta W that you're trying to achieve, and that's what that red means there, and you allow it to vary 1, 2, 3x of delta W. So this isn't of the entire W, but delta W. What is the result? This is just kind of a summary because we've done several measurements. But I mean, you can actually, the interesting thing that we found is, at least from the point of view, if you're varying up to 6 or 7 times the delta W that you intended, you actually can still, it doesn't affect your accuracy that much. Now, the disclaimer here is that actually the delta W's that you're intending are still very small compared to the actual entire weight. And so when you translate this to resistances, it's a good thing, but it doesn't, the resistance amount that you can move for resistance is much more than what we're showing here. And this is all for training, by the way. So a lot of times people will show data just for processing, and the actual processing is much more noise resilient than the training. But this is if you're using these devices when you're training. So I think in summary, really the main thing I want to say is that I do think new type of hardware is going to be useful for neuromorphic algorithms, and in particular because there really is only so much SRAM that you're ever going to be able to put on a chip, even with the few latent generations that you have. And integrating DRAM on a single chip, you can't really stack it, and so there's a limitation there. So if you need to combine a large amount of data with a very significant amount of processing with essentially low power routing, I think resistive memory accelerators will save you a huge amount of power. So anyway, the next step is to create a, nail down the architecture and create a complete model of this. So, okay, that is it. Any questions?